Wishing you all, I'm Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, I wish to tell about the Ruby lasers. In the last class, we have seen components of lasers. So, in that, we have seen source energy, active medium, and then optical cavity or optical resonator. So, in this class, we are going to see lasers. In that lasers, we are going to see the first solid state laser, which is Ruby laser. So the Ruby laser was the first solid state laser which is fabricated by the Maiman. So Ruby laser is a solid state pulsed one and it is a 3-level laser. It consists of cylindrical shaped Ruby crystal rod. So the cylindrical shaped crystal rod having the length varying from 2 to 20 centimeter and the diameter varying from 0.1 to 2 centimeters. So we have a Ruby crystal rod which have cylindrical shape. So this cylindrical shape Ruby crystal rod have the length 2 to 20 centimeters of length and the diameter it has 0.1 to 2 centimeters. And the end faces of this Ruby crystal rod is highly flat and they are parallel to each other. One of the face is highly silvered and the other face is partially silvered, so that it emits or it transmits 10 to 25% of incident light and reflects the rest so as to make the rod resonant cavity. So basically, Ruby rod or Ruby crystal is made up of aluminum oxide, Al2O3, aluminum oxide, which is doped with 0.05 to 0.5% weight of chromium oxide atoms. So these chromium atoms serves as activators. So the chromium atoms which are doped in the place of some of the aluminum atoms is replaced with chromium atoms. So these chromium atoms serves as activators. Due to presence of this 0.05% of chromium, this Ruby crystal appears pink in color. So the Ruby crystal is placed along the axis of helical xenon flash lamp or krypton flash lamp of having high intensity. So this Ruby crystal rod is placed along the axis of helical xenon or krypton flash lamp of high intensity. So like this we have helical xenon flash lamp. So when coming to the construction of Ruby crystal or Ruby laser, so this Ruby, that is aluminum oxide plus chromium oxide atoms or combined together. So this Ruby is a crystal of aluminum oxide in which some of aluminum ions are replaced by the chromium ions. So here some of the aluminum ions is replaced with chromium ions. When the doping concentration of chromium ions is about 0.5%, 0.05%, the color of the rod, Ruby rod, becomes pink. So the active medium in Ruby rod is chromium ions. So the activators in this Ruby rod is chromium ions. So in this ruby laser, a rod of 4 centimeter long and 5 millimeter diameter is used, and the end of the rod are highly polished. So it can be vary, the rod length may be vary 4 centimeters long and 5 millimeters diameter here, and is used for the ruby crystal rod. And the end faces of this rod is highly polished. Both ends are silvered, so the one end is fully reflecting and the other end is partially reflecting. The ruby rod is surrounded by helical xenon flash lamp tube, which provides the optical pumping to raise the chromium ions to upper energy level. So usually the atoms will be in the ground state, lower energy state. So here the ruby rod is surrounded by xenon flash lamp tube. So by this helical xenon flash lamp tube, we are giving some light. So because of that optical pumping, because of that light, the chromium ions get energy, excites to higher energy levels. So that we are using optical pumping to raise the chromium ions to the excited state. So by the optical pumping, the chromium ions excited to the upper energy level. The xenon flash lamp tube, which emits intense pulses, lasts only few milliseconds, and the tube consumes several thousands of joules of energy. The xenon flash lamp tube emits intense pulses that would last only few milliseconds, and the tube consumes several thousands of joules of energy. Only a part of this joules of energy is used in the pumping mechanism. That is, part of this energy is used to pump the chromium ions. Remaining will goes as heat to the apparatus, which should be cooled with cooling arrangements. So through the xenon flash lamp tube, the chromium ions get excited to the higher energy states, and energy remaining energy will be heat up the apparatus. Remaining energy heat up the apparatus. So this heat should be cooled with the cooling arrangements. So here in this, the ruby laser setup, you can see the ruby laser rod is placed along the axis of helical xenon or krypton flash lamp tube. The ruby rod, the crystal ruby rod, is placed along the xenon discharge tube or else krypton flash lamp tube. Or else xenon flash. So here there is a ruby crystal rod. In this rod, this rod is made up of aluminum oxide and then chromium oxide ions. So here some of the aluminum ions is replaced with the chromium ions. So as it is made up with aluminum plus chromium ions. So this rod is placed along the axis of helical xenon flash lamp tube that were connected to some power source. So this ruby crystal rod have two faces. So the end faces of this ruby crystal rod is highly silvered. That is, one end of the face is fully reflecting, another end of the rod is partially reflecting. So these two end faces are flat and parallel. The end faces of the ruby rod is flat and parallel. One of the face is highly silvered and other face is partially silvered. That's it. Fully reflecting end. Another one is partially reflecting end. So here, when we give some power source, then through the xenon flash lamp tube, it gives intense pulses. So because of that, optical pumping mechanism take place. So when it gives pulses, through that pulses, the chromium ions in the rod get excited and jumps to the higher energy levels. Here some of the energy is used to raise the chromium ions to the upper energy levels. Remaining energy will heat up the apparatus. So that should be cooled with this cooling arrangements. So when the ruby rod, when the atoms are more enough, that is, because of stimulated emissions takes place in this ruby crystal rod. So when there is a high amount of photons are emitted, then through this partially reflecting end, it can be coming out. So the light, the laser beam comes out from the partially reflecting end. How it is working, how the ruby laser works. Ruby crystal is made up of aluminum oxide as a host lattice with small percentage of chromium ions replacing aluminum ions in the crystal. Chromium acts as a dopant. So a dopant actually produces lasing action while the host material sustains this action. So chromium ions acts as a dopant. So this produces the lasing action and host material, it sustains this action. The pumping source for a ruby material is xenon flash lamp, that is optical pumping, which will be operated by some external power supply. Chromium ions will respond to the flashlight having wavelength of 5600 angstroms. When these chromium ions are excited to higher energy level E3 from E1, the population in E3 increases. So, through the optical pumping, chromium ions get excited to the energy level E3. So, in this diagram, this is E1, E3, this is E2. So, when these chromium ions get excited, this chromium ions jumps to E3 energy level from this E1 energy level. So that population in the energy level E3 increases. So to achieve stimulated emission, it is necessary there should be population inversion. So population inversion is nothing but more number of atoms in the higher energy state. Usually, N1 is greater than N2. The atoms in the lower energy level is greater than the atoms in the higher energy level. But population inversion means that N2 is greater than N1. To achieve population inversion, higher energy level should be more number of atoms comparing to the lower energy level atoms. So the number of atoms in the higher energy level is more comparing to the lower energy level, then it is called population inversion. So when chromium ions are excited to higher energy level E3 from E1, the population of this E3 energy level increases. Chromium ions stay at E3 energy state for a very short time of the order of 10 power minus 8 seconds. This 10 power minus 8 seconds is the lifetime of an atom in the excited state. So chromium ions stays at the E3 energy state up to 10 power minus 8 seconds. Then after this lifetime, they drop to the energy level E2. Energy level E2. So E2 is a metastable state where the ions having longer lifetime. So they drop to the level E2, which is metastable state of lifetime 10 power minus 3 seconds. Here the energy level E3 is rather a band which helps the pumping to be more effective. The transition from E3 to E2 are non-radiative in nature. So while the transition from the E3 to E2, it is a non-radiative transition. that is radiationless transition takes place from E3 to E2 energy level. So the transition from E3 to E2 are non-radiative in nature. During this process, heat is given to the crystal lattice, hence cooling rod is an essential feature in this method. So these photons travel through the rod. If it is moving parallel to the axis of the crystal, is reflected back and forth by silver ends until it stimulates an excited ion in E2 and causes it to emit fresh photon in phase with the earlier photon. So this photon travels through the rod, and if it is moving parallel to the axis of the crystal, it is reflected back and forth by the silver ends until it stimulates an excited ion in E2 and causes it to emit fresh photon in phase with the earlier photon. So this stimulated transition triggers the laser transition, and this process is repeated again and again because the photons repeatedly move along the crystal being reflected from its end. So the photon thus get multiplied. When the photon beam becomes sufficiently intense such that part of it emerges through the partially silver end of the crystal. So in this diagram, ground state energy level E1, excited state energy level E2, E3. So we are giving some energy in electron volts. Then pumping mechanism takes place with having 5500 angstroms. The chromium ions get excited as the chromium ions are activators. So chromium ions get excited to E3 after 10 power minus 8 seconds. This transits to E2 energy state, which is called metastable state. So here this transition E3 to E2 is a radiationless transition. Here in this metastable state, it has a lifetime of 10 power minus 3 seconds. So it would get stimulated by the photon. So as to that photon be moved back and forth between the fully and partially end phases. When the intense is high, when at the high intense, the emission comes out from the partially silver end. So after here, this atom transits to ground state, which is a phase. Here we get laser transition. So chromium ions get excited through the optical pumping. So chromium ions get excited to E3 energy level. Then, after 10 power minus 8 seconds, they transits to E2 energy state with radiationless transition. In this process, in this transition, E3 to E2, heat is generated. So, that heat can be cooled with the cooling rods. When the photon travels through the rod, that photon get reflected back and forth between the end faces. These are the two end faces of the ruby crystal rod. So that photon is reflected back and forth by the silvered and partially silvered end faces until it stimulates an excited ion in E2 and causes it to emit fresh photon in phase with the earlier photon. So, a stimulated transition triggers the laser transition, and this process is repeated again and again because the photons repeatedly move along the crystal being reflected from its end partially and silver ends. So the photons are thus get excited or multiplied, not excited. They get multiplied when the photon beam comes sufficiently intense. It emerges from the partially silver end. So here in this ruby laser, it has some drawbacks. So the laser requires high pumping power because the laser transition terminates at the ground state, and more than one half of the ground state atoms must be pumped to the higher state to achieve population inversion. The laser requires high pumping power because the laser transition terminates at the ground state, and then more than one half of the ground state atoms must be pumped to the higher state to achieve population inversion. The efficiency is very low. The ruby crystal laser. In the ruby crystal laser, the efficiency is very low. Only the blue and green components of the flashlight, green and blue components of the flashlight are utilized and the remaining are unused. It is a pulsed laser. The laser output is not continuous but occurs in the form of pulses of microseconds. That's why we tell it is a pulsed laser. And three-level laser. So three energy levels. So when chromium ions get excited, it went to A3 energy level. From A3 to E2, radiationless transition. So E2, in this E2 state, it would stay there up to 10 power minus 3. So this photon moving back and forth until it triggers with some stimulated transition. So then they fall back to the ground state. So at high emission, it would comes out as a laser beam with high intensity in phase. So we'll get laser output from the partially reflecting end phase. So here we get the laser beam. So as we are encountering the drawbacks in this ruby crystal rod, uh, ruby crystal laser, we are going to see some more laser, that is helium, neon, laser, neodymium, yttrium, aluminium, garnet lasers, and semiconductor lasers also be there. So as it has drawbacks, we are going to produce some other experiments. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.